Good day everyone, and welcome to the 6th week of the differential equations class. Yeah, I have to apologize. This week material is going to be a bit boring and dry again. It's mostly calculations. There is even a warning here. Well, I wrote that today's lecture will be conducted on the visualizer, meaning that that there's going to be a lot of computations that I'm going to write on this screen, and but I'm not going to type them. So if you want to follow the lecture, you cannot read the slides. You'll have to watch the video. Alright, so in order to understand today's lecture, you need to review complex numbers. You'll need to recall how to solve systems of linear equations. And you'll need to review the previous lecture. Alright, but let me help you to review the previous lecture. Last week we discussed second order homogeneous linear differential equations with constant coefficients. So in order to solve such a differential equation, you need to set up the characteristic equation first. So the characteristic equation is just an algebraic equation with an unknown r and the same coefficients. So if it has two real roots, then we are done. So then any solution of the ODE is going to be a linear combination of the exponential functions. One more thing that we learned last week is that there is this notion, the Wronskian. So let me maybe recall the notion of a Wronskian. So the Wronskian of two functions, f and g, is the determinant of the following matrix. So you need to, the first row of the matrix is the two functions, and the second row are the derivatives of the two functions. So using the Wronskian, you can verify if functions are linearly dependent or independent. Last week we were not able to figure out what to do if either we have a repeated root or complex roots. So besides, last week we introduced this structure theorem, so that the set of all solutions of a second order homogeneous linear equation is a two-dimensional vector space. Essentially it means that if you find any two linearly independent solutions, then any other solution is going to be a linear combination. But so let me just mention it again, that this theorem works regardless whether coefficients of the differential equation are constant or non-constant. It doesn't matter here. But it's just that if the coefficients are non-constant, then there is no general way to find two linearly independent solutions. But if the coefficients are constant, then there is an easy way to find two linearly independent solutions. But however, even if the coefficients are constant, there is no obvious standard choice of a basis. So here is an example. Sorry, yeah, the example will be later. So given any particular basis, then any other basis can be constructed from the given basis by multiplying with an invertible matrix A. So this is material from linear algebra. Okay, so let me give you an example now. Right, so this is an example of a homogeneous equation with constant coefficients actually, but if you write down the corresponding characteristic equation, it's going to be r square plus 1 is 0. And this equation does not have real roots, so the roots are complex. So which means that we didn't discuss how to deal with this type of equations in general, but of course in this case it is a fairly simple equation, so you can guess that sine and cosine satisfy the equation, right? So for example, cosine t prime is minus sine t. Cosine t second derivative is the first derivative of minus sine t, so it is minus cosine t, and of course cosine t plus minus cosine t is 0, so it does satisfy the equation. But here is another basis, so in the same way this would be also a basis, right? You can easily check it. So anything that you can think of that is combined, well, made of cosine and sine is going to satisfy this differential equation. So how can we check that this alternative basis is indeed a basis? I mean, one thing that we can do, we can calculate the Wronskian of sine of pi over 4 plus t and sine of pi over 4 minus t. Well, but let me just give you the linear algebra method. So we can express these two functions as linear combinations of these two, right? So these two can be expressed as linear combination of these two. And here is how. So you need to recall the trigonometric equations for the sine of the sum of the two things and the difference of the two things. And then if you try to calculate it, then you will see that these two functions can be indeed expressed as sum matrix times cosine t and sine t. So in this case the matrix is 1 over root 2, 1 over root 2, 1 over root 2, and minus 1 over root 2, right? So in order to construct this matrix, I just read off the coefficients here. And of course you can easily check that the determinant of this matrix is going to be 1 over root 2 times minus 1 over root 2, so it is minus 1/2, and minus, again, 1/2, minus 1. So the determinant is indeed non-zero, and which means that the two new functions are, again, linearly independent, and therefore they constitute a basis.